Hello, everyone. I'm Susan Nash, AAPG. Delighted to be here and to welcome you to week 16, Battery Tech and Critical Minerals. We have a wonderful lineup today. We have a group of individuals who are experts in this area, and we'll have Edith Newton-Wilson of Rock Whisperer, Paul Anthony Thomas of Custom Private Equity, Ray Donelick of Apatite, Ashley Zumwalt-Forbes of Black Mountain International, and want to welcome everyone to our event tonight. So basically, I would like to invite Edith right now to share her screen, and I will stop sharing mine, and welcome. Perfect.
All right. Can everyone hear me?
Yes.
Okay, great. I'll get started. I'm really delighted to be here, and those of you who know me understand that I really love taking the big picture part of the story, so this was the perfect fit to sort of introduce the topic of critical minerals for energy storage, and I'm really going to focus on that energy piece, since we are all energy professionals gathered here today. Of course, there is also another world of critical minerals used in the Internet of Things, in all of our devices and handheld electronics, but I'm really going to focus on those that are critical for energy storage going forward. This introductory slide is a flake of graphite. It's an SEM photograph, courtesy of a colleague of mine, Ty Dinwiddie, and it's really indicative of the scope and scale of where we're going to go from global energy demand down to the nanoscale of energy storage. And I want to start out by reminding everyone of what the rest of the world, and in fact most of the largest corporations in the developed world and in the developing markets are using as their measuring tool these days, written into their reporting, is tracking progress toward the 17 Sustainable Development Goals. And make no mistake about it, this is not about feeling good about hugging trees. This is about business. This is about improving profitability with meeting these goals, and it's why so many companies from Walmart to Tata are using them as their measuring stick. And of course, all of us have been involved in the energy goal for our entire careers working in oil and gas. It's our ultimate goal to ensure access to affordable, reliable, sustainable, and modern energy for everyone on the planet. And we're just finding ourselves in a position today where the energy that we're using and helping provide access to is changing really dramatically. And I'm not going to go into what I talked about the last time I worked with Susan on one of these, the whole economic underpinning of what's happening in the energy transition, the relative abundance of renewable energy, the drop in cost of renewable energy, and the efficiency improvements. But I just want to put this snapshot of the most recent global energy data up to remind you that we're kind of in the middle of an unplanned experiment on energy usage worldwide. And what we're seeing, these data are all from the International Energy Agency's most recent report in April of 2020. And what we are seeing, in addition to a significant drop in CO2 because of the lack of energy usage, and that has recovered somewhat in recent months, we are also seeing a continuation of the drop in demand growth that we were already seeing in 2019 in the developed world. We're seeing that extend even to growing energy markets. Demand growth is slacking off. And we're seeing, particularly in coal, oil, and natural gas, a significant drop predicted for 2020 relative to 2019, with only the renewable component actually having a little bit of growth relative to last year. And that, again, is being driven by productivity increases, cost reductions, et cetera. So I just put this in front of you to kind of remind you of the big global picture. But getting to the energy storage component of this, this curve should be familiar to anyone who's looked at Silicon Valley investing over the last 20 or 30 years. You know, this is that classic tech explosion curve of cost, which is on the left-hand axis in light blue, just dropping through the basement, while productivity or production or whatever other measure of growth you want to plot is screaming to the surface. Now, this graph is for lithium-ion batteries, and it looks at price per kilowatt hour in light blue dropping and production rising in gigawatt hours on the right. So what we're seeing, again, we've passed that curve crossing point where the cost is low enough to drive this explosion in productivity. And this particular graph from WoodMac is, you know, it might as well be from the Pleistocene because it's from November of 2019. Since this graph was plotted, first of all, you'll notice that manufacturing capacity over 10 years has grown 85% just to today. And then it was predicted as of this graph to go up to just over 700 gigawatt hours by 2028, by 2026. But the most recent data I've seen in looking at how much energy storage is contracted out there for electric vehicles and for long-term energy storage looked at going to 2 terawatt hours by 2028. So we can't plot these graphs fast enough. The numbers just keep growing. The most recent data I saw just a few days ago documented 400 terawatt hours being added in Europe alone in the next 3 years. So that's right here. So again, just so you recognize, this is explosive growth, almost undocumentable in the energy storage world. So what's at the bottom of all of this? Well, I want to take you back and introduce the sort of father of the lithium-ion battery because he is a fascinating guy. This is the picture of John Goodenough, and he is at the University of Texas in Austin, still trying to build a better battery. He was born in 1922 in Germany to American parents. He attended Yale. He was a military meteorologist during World War II. He received his Ph.D. in physics at the University of Chicago, was a researcher at MIT, head of inorganic chemistry at Oxford. He received a National Medal of Science, the Fermi Award, and at 97 years old, he became the oldest Nobel laureate in history, receiving the Nobel Prize in Chemistry in 2019. And he's still working to build better batteries. He was also one of the original team that developed RAM, random access memory, remember that? And he doubled battery capacity because he's the one who dreamed up this layered silicate design of cathode and lithium, of cobalt and lithium in the battery cathode that is so key to energy storage and recharge and lightweight in lithium-ion batteries today. Now he's working on glass electrolytes instead of the liquid electrolytes that currently dominate the battery future. I am not a battery chemist, but I can tell you that the way these things work is that lithium ions flow back and forth through the electrolyte, while electrons charge and discharge on the external circuit. So key to that for us as interested in the minerals is that we need to be conscious of the bulk of the minerals are composed of, in the anode, and in most cases graphite, and then a smaller volume of minerals in the cathode, in this case lithium and cobalt. So which metal is in that battery really matters. And what I mean by that is each of these metals and how they're interlayered in a mineralogical sense and where they sit on the periodic table impacts how much energy they can store. So if we look at energy density, or essentially the amount of energy stored in a given material per unit volume or mass, we can see which metals contribute to a bigger bang for the buck. And you can see the progression from nickel cadmium to nickel manganese to lithium ions, giving us more and more energy storage per volume of material used. So this sort of search for higher and higher energy density is what is occupying the battery research world right now. One battery tech company with which I work is working on an advanced material that has been tested to have an energy density in parity with hydrocarbons, that is around 12,000 watt-hours per kilogram. So a truly phenomenal step. And these sorts of research projects are going on all over the world, so this picture will change dramatically. So again, not only is it a lithium-ion battery across the board, but there is a difference in what metals are used in that lithium-ion battery. And not only does it make a difference to the energy density, it also makes a difference to the carbon footprint to produce those metals. And what we're looking here is at 3 different kinds of batteries, and the carbon footprint calculated in grams of carbon dioxide equivalent per kilogram, sorry, that should be kilograms, for each of these different kinds of batteries. And you can see that these nickel cobalt batteries are quite expensive in terms of their carbon footprint, and they are the ones that are used in Tesla. So if you're driving a Nissan Leaf and charging your car off of solar or a natural gas or a hydro grid up in Canada, you've got a very, very low carbon footprint. If you're driving your cobalt-rich Tesla and you are charging it off a coal-fired power grid, you actually have a bigger carbon footprint than an ICE vehicle, an internal combustion engine vehicle. So again, which metal matters? It matters for energy storage, and it matters for carbon reduction as well. So this is why there's so much change in the market from metal to metal. I'm going to pick on one and show you just a couple of things about how it's distributed and what we look for. And I'm going to start with lithium here. The little red and pink and yellow dots are all lithium deposits from the USGS database. So these are not mines. These are just places where someone has gone out and noticed a lithium accumulation of some sort. The reds and pinks are hard rock lithium, mostly spodumene and pegmatite. The yellows, like here in South America, are lithium brine deposits and salars, where the lithium is concentrated in salt deposits. So the dark-colored countries are the countries in this mined production graph, again from USGS data. And the story of lithium is very similar to other critical minerals in that there is one country that dominates lithium mining, and that is Australia. And Australia mines close to almost 2/3 of the world's lithium from spodumene hard rock deposits. And then a close second are the deposits down in the lithium triangle. But there's really, and what I want you to also know, and these are just market figures from Simon Ward's at Benchmark, is that we're looking at global demand for lithium for battery storage alone, just for EVs, forecast to triple by 2023. And again, these are old data. But almost more important to look at than where lithium is mined is where it is processed and where it is manufactured. And I'm going to come back to this. It's a full supply chain story when we talk about critical minerals. Because even though most of the lithium is mined here in Australia, in this dark red area, the hatchered countries are where lithium is processed. And actually, in Chile, only a little bit of pre-processing is done. Almost all of the lithium from all of these different mines around the world is processed in China. And then overprinted on that are these dots that reflect the pie chart in size, showing that 2/3 of the batteries are actually manufactured in China as well, with a chunk of that being mainly Tesla in the United States and the rest in South Korea, Japan, and Europe. So this is not just a story of where metals are mined, but in actual fact, it's this metals, turning that lithium salt into the perfect chemical mix for each individual battery, taking the graphite and making it into a bespoke material that works for the cathode of the BMW or works for the cathode of the Tesla or works for the cathode of the Catwell battery. This is the place where the value is added, is in the processing piece. So very, very different from our world of oil and gas. And then there also are steps in cell production and module assembly before we get to the original equipment manufacturers. So this entire value chain requires engineering skills, geoscience skills, certainly in the mining side, and then material engineering skills, material science skills, definitely in the processing piece. And it's not just lithium, of course, it's cobalt, graphite, a bunch of other stuff, but mainly in terms of volume. We're talking about graphite is the big heavy lifter in batteries. So if we look at similar maps, and I'm not going to go into the details of this, but you can see there are similar dominant players like cobalt, 2/3 of it comes from the DRC, mined graphite, 2/3 of it comes from China. But again, most of these metals are processed predominantly in China. So this full supply chain is where our skills are needed in the critical mineral space. Now, the way these deposits are evaluated, if we look just at that sort of mining side, looks very familiar from an oil and gas perspective. There is a preliminary assessment followed by a pre-feasibility study, followed by a full feasibility study that where costs to do the studies and the evaluation increase while the risk is reduced. Now, what is really interesting about mining pieces is, and there are very rigorous controls on how these processes are done, is if we look at this figure, this green line indicating how many projects make it through each stage, many, many, many projects never get past being one of those little dots on the map. They're only just deposits that we have no idea whether they'll be economic or not. And very, very few actually make it to a feasibility study to be a mine. The last thing I want to show you are just some very back-of-the-envelope kind of cartoon calculations of the difference in the cash flow models once you do get to that project stage and past that feasibility gate for mining as compared to oil and gas. And for this oil and gas model, I think I've just pulled these data from some published pioneer data out in the Permian Basin, and I've shown you, kind of an area of a few hundred acres over which this project would sort of lay. And in this case, we're looking at, investing $175 million in capital. The payback is almost immediate. The project life is fairly short because, in the out years, you're not making much oil. But the NPV is quite good. And again, what investors loved about the oil field is this energy from the reservoir pushing that payback and giving up all the value in the early years. In contrast, in a project that a colleague of mine has been working on over sort of a similar area of a deposit, if we're looking at a mine model of capital investment with a similar NPV of around $150 million over the course of the life of the project, what we see is a much lower capital investment up front, but also a much slower and steadier positive cash flow in the out years and a long, long payback. So for investors to sort of switch, from oil and gas with its reservoir energy to a mine model, it's a very different piece to get used to. And remember that no matter what comes out of this mine model, all the value is really added in the processing. So a friend of mine, Lucy Crane, who's stripping lithium from Cornish geothermal brines related to the old tin mines, has a phrase that I just love. Anything that isn't grown, you look around the room, wherever you're glancing, anything that isn't grown, wood, grass, wool in your sweater, is mined. So we all need to kind of get much more familiar with our old friend, the periodic table, because if it isn't going into a battery storage device or some thing in the Internet of Things, it's going to be going into new buildings, livable cities, road infrastructure, transportation infrastructure, and all of these metals and critical minerals for energy storage are a huge part of that. So I leave you with this slide, which I think represents, kind of brings us back to that first slide of the Sustainable Development Goals. Not only are we looking at mining new components for energy storage, we're also looking at using renewable energy to mine those materials and process those materials with lower carbon footprint. This is the Atacama, Lake Atacama in Chile, where Anglo American is floating solar on their tailings pond to give them cheap, clean energy to run the mines underground, and also reducing evaporation from the tailings ponds at the same time. So it's a great symbiotic relationship. So that's all I have to say at the moment. I'll turn the program over to the next speaker, and looking forward to the discussion at the end.
Thank you, Edith. That was really great. And seeing the floating brine pits at Atacama makes me think a little bit about why we don't do that with produced water. But at any rate, it's such a great model. At any rate, well, thank you. It was fantastic. I want to take a moment at this time to introduce Dr. Larry Davis, who's with us, who's from Texas A&M Texarkana. He's a professor of economics, former dean of the college, and his specialty is strategic planning. So, Larry, would you like to talk to us a little bit about basically just a few pointers to think about when we're making massive changes, like going from one type of energy to another, some of the strategic planning implications?
Well, I don't want to be boring and repetitive. You're making the same comments every week, but I will emphasize one point in the strategic planning process. A strategic plan is based upon information that you have available at the time that the plan is prepared, and after assessment of external influences and internal influences. We're having a lot of external influences with coronavirus and some other things that's causing the pivoting or encouraging the pivoting that we've talked about. And I made some comments earlier. I don't know if we had started yet. No, we hadn't started yet when I made those comments. That I saw a report today that businesses were hesitant to allow workers to work from home because they didn't trust their productivity and commitment to their work. But now that they have a track record, the report said up to 30% of employees, certain categories of employees, would continue to work from home after the virus is over. So we're having some major cultural changes. And anyway, when it comes to your companies or any other company to have a good strategic plan, its value is enhanced by having a monthly or quarterly, probably more frequent than quarterly, to assess those external influences and make adjustments to goals and objectives and budgets as deemed necessary. It's important that it be looked as a dynamic document and not one that's set in concrete.
Oh, that's great. That's really a really good way to look at things, and it's very helpful, especially as we move from Edith to our next speaker. Our next speaker is Paul Anthony Thomas with Custom Private Equity, and he's going to talk to us about investing in oil and gas and also investing in critical minerals, lithium being one. So welcome, Paul, and if you'd like to share your screen, that would be fantastic.
Yeah, thank you very much, Susan. I appreciate being here this evening, and I'm going to be a little redundant in what Edith talked about, but I'm also going to talk about a whole lot of other critical minerals. As the world changes and we pivot away from oil and gas, a lot of us don't want to do that, and I'm particularly one of those people. I'm still out buying oil and gas production today. I think oil and gas is here for another 20 years at least. Our actual projection, if we do a mass balance on it, is we think that oil and gas will make up about anywhere from 5 to 10% of the energy stream in 2070, and that's just my view, the view that we've done over some research we've done over the last 2 decades. And So that's kind of what we look at, but we are phasing out of oil and gas. And I know a lot of people on the call don't want to hear that, but it is true. And if you don't believe it, just kind of watch the statistics and you'll certainly understand that. So I just shared my screen, and we're going to talk about the list of what they call critical minerals in the United States. A few years ago, the government decided they needed to make a list of minerals that were critical to the economy in the United States, and they call them critical non-fuel minerals. And I'm going to talk about the kind of the origins of these and where they're located. Edith talked about where lithium and cobalt and those kind of things, those are both on the list, are located. But I'm going to talk about some of the other minerals, and we're going to kind of go through this right quick. I've got a little bit to share. So my periodic table is more of an economic periodic table than Edith's was. The red squares on this periodic table are highly critical minerals. They're things that are very much in demand or going to be in demand, and they're critical to the infrastructure of the globe pretty much. The ones that are in tan are in the exploration mode. We consider those to be things where you can find opportunity by going out and finding the resource. Production resources and exploration of the blue squares, manganese, iron, cobalt is one of the ones that Edith talked about a minute ago. Nothing's better than a really nice little cobalt mine if you want to make some money out of the world. Lithium is also a really good commodity to go look for and go try to find. Then we have, in the green squares, we have resource plays that are going on. So these critical minerals, they all basically come from host metals. And there's a list of 10 host metals there, including aluminum and tin and iron. So if you want to find gold, for instance, you would go and find, or if you want to find silver, you would go and try to find where there's quite a bit of gold. And there's going to be silver associated with that. Platinum's the same way. You're going to go find palladium where you find platinum. So those are the host metals, and you're going to find the other critical metals surrounding those, and as a byproduct of the processing of them. Copper in particular throws off a lot of these critical minerals. So this map is a very interesting map, and I'll be able to provide these or give these slides to anyone who wants to see them. I just have amassed them over the last couple of years and been working through this, but these are countries that actually supply the United States with different chemical compounds and different chemical elements. And the ones in dark red are the ones that supply from 19 to 25 of the critical, more than 50% of our critical needs. There are a lot of minerals, and we'll see this on the next chart. Everything that's in the solid blue lines there, they all come from other countries. So cesium, fluorspar, graphite, which is one that Edith mentioned a minute ago, they all come from other countries. Although there are graphite mines in the U.S., there are no active graphite mines in the U.S. as far as I know. Manganese is another example. China is the #1 supplier, the only supplier of rubidium. I've got these listed out where you can see them. Zinc, we get about 85% of our zinc from Canada, Mexico, Peru, and Australia. And we're going to look at these maps, and I'll be glad to give these to anyone. It's very interesting to look through this stuff. We get about half of our lithium from other countries down there. We see that. Chile, Argentina, and China is the #1 producer. So here's aluminum. Although aluminum's kind of trying to be phased out, it has a lot more uses than most other metals, but China is the #1 producer of aluminum in today's world, and aluminum sells for 75 to 65 cents a pound. So whenever we start seeing metals and elements that are priced out in pounds and ounces and grams and kilograms, we start thinking that there's probably going to be some opportunity around those. There is opportunity today. Aluminum is the #1 recycled metal around the globe, and it's extremely valuable actually in today's world. Nothing's nicer than a nice bauxite mine. So antimony is the next one, priced about $5 a kilogram. Anytime we start talking about pricing things in kilograms, we're going to look for some opportunity there. Antimony is used in batteries, and they use it as flame retardants. The next one's arsenic. Unfortunately, arsenic is considered to be a contaminant in today's world. It is a critical mineral. We do need it, but anytime you talk to virtually anybody about arsenic, they're going to talk about the contamination side of the coin, and that's what this map is all about. This is what the estimation of groundwater contamination by arsenic. Arsenic is a very, it's a soluble type chemical, and it's located in lots of different places. So this is what groundwater contamination is expected to look like around the globe from arsenic. Barite is tied to the oil and gas industry. The oil and gas industry is the prime user of barite, and they use it in oil and gas drilling, as everybody in the audience knows. Most of the barite comes from the US, China, India, and Morocco. It's kind of interesting. You can see in this barite production chart, it actually tracks the world rig count. That's what this chart is here, the figure 1. So, barite sells for $1.25 a metric ton. So, there's nothing nicer than a nice barite mine, but if you have to price things at $1.25 for 2,200 pounds, that's you got to do a lot of work to get there, to get to any kind of real profits. Well, the interesting thing about it, barite is used in medical facilities, and it absorbs X-rays and gamma rays, which is always a very interesting thing. So there's some high uses in the medical world. This is barite mines around the globe. You see there's quite a lot of barite mining in North America, and barite going actually all around the world. So China's got a lot of it. Beryllium is a very interesting thing. We see a lot of opportunity in beryllium, and then one of the main reasons is that it's present in a lot of places, and it sells for $660 a kilogram. That's very interesting. It's mined in Utah. It's also mined in China. Go out in the world and find yourself a nice beryllium metal mine, and you're going to be a wealthy guy. That's all I got to say. It's kind of like hunting elephants. We used to hunt elephants when I was younger, and this is going out and trying to find beryllium, and finding productive beryllium would be an elephant hunt. It would be a lot of fun for a geologist. One of the things I like about the critical mineral field is that if you want to travel around the world, this is a great way to do it, because these minerals are located on every continent, almost every continent except Antarctica and the Arctic. Bismuth is another one, sells for $3.40 a pound, mostly made in China, imported from China. China's the #1 producer, used in medical research and atomic research. Bismuth is a pretty important mineral for the atomic world, which we're coming into. Cesium and rubidium the same way. This is an interesting map. This is a map of contamination around the world for cesium, and it's always viewed as, since it's radioactive, it's viewed as a contaminant for sure. And you see in North America, up in North America, up in Canada, and around the contamination around Chernobyl, and then the 83 over there in Japan is another kind of high number for this. So they've had releases of cesium in those areas. But cesium bromides and the carbonates, they sell for $101, $110, $118. I mean, it's a pretty valuable commodity. There was one company in 2019 sold 1 gram of cesium for $63. That was a kind of a record, but it's a very valuable mineral. Chromium, highly recycled. South Africa is the #1 producer of chromium. India #2, and #3 is in Central Asia. Most of the chromium in the world comes from South Africa. There's a good chromium and a bad chromium. And when I would work for the EPA back in the 90s, we always had a battle with chromium being used as a algicide, and it was a highly contamination. It contaminated the soils and waters around drying towers and cooling towers in a tremendous way, and it was actually a really hard chemical to clean up. But it is a very major thing, and we have to have it for our health. Your body has chromium in it, so the good kind of chromium is a very important metal. Cobalt, same way. It's used, Edith was talking about it earlier, it's very critically important in the lithium world. I do think that we're going to phase over the next 50 years, we're going to phase out of the lithium battery phase, and we're going to phase into some sort of glass type batteries. They're working on that technology today, but I think it's 10, maybe 15 years in the future. There's a lot of people out there that disagree with that, but that's what I think. In March of 19, the price of the cobalt was about $17 a pound. We'd like to have a good cobalt mine under our belt if we could find one. Fluorspar is used for hydrofluoric acid. They use it in gasoline, aluminum, welding rods. China's the #1 producer of fluorspar. Mexico produces quite a lot as well. The United States doesn't produce any. We import 100% of that. Sells for anywhere from $250 to $405 a metric ton for acid grade. Very interesting chemical. There's a picture of it. We actually closed the last fluorspar mine in North America in 1995, but that doesn't mean there's not some more to be found. I mean, as you know, minerals, you can go out and find minerals just on a whim sometimes. You have to use a little science behind that. So gallium is a very interesting chemical, very interesting mineral. It's mined in France. The highest grade sells for $400 and $500 a kilogram. Low grade stuff sells for $150 a kilogram. This is where gallium is found around the globe. Not all these things are mines, but it's amazing how much of it's found in Europe, in the mountains of Europe. Germanium is another one. We see tremendous opportunities in germanium. Year-end price for germanium was $1,150 a kilogram in 2000. World germanium consumption has been greater than primary production in recent years. We see an opportunity here for people if they want to go out and try to find some tailings to mine or recover or do some recovery on this. Increased recycling has provided adequate supplies, but the supplies are running low of this product. Graphite, this is one that Edith was talking about earlier. Synthetic graphite, which is a new different form of carbon, can sell for $20,000 a metric ton. That's an incredible price. But amorphous, $430 a ton. Demand is, as lithium batteries grow, demand for this product is going to go through the roof. And you saw on Edith's slide a minute ago that it's scheduled to increase by tenfold over the next 10 years or so. It's used, the interesting thing about graphite, it has metal characteristics and characteristics of a non-metal. So that's a very interesting, we see a boom coming in that product, and there's a lot of it around. This is graphite mines. She showed you a map of this. Graphite deposits and mines around the world. Helium, I've had a couple of helium deals come in front of me in the last couple of years where they're recovering helium from natural gas. The natural gas in the Texas Panhandle is extremely high in helium concentrates. But if you had a really great helium source, you could actually create a tremendous amount of wealth in a hurry. Current law, for instance, is going to require, they're going to change this law, I think, but it requires that the U.S. government, who's controlled the helium market for a number of decades now, they're going to actually require that they sell all the helium assets that they own. So that we see that as an opportunity. We're going to try to do something about that. We see a boom in this marketplace. If you think natural gas is cheap, helium's not cheap. 2020 price is $210 an MCF. If you could find some really nice helium deposits, and there are helium, almost pure helium deposits around the globe. So it's not that they can't be found. Here's helium maps. Russia's a primary producer. The United States has the largest helium resources to date, but that's not to say that there aren't other helium deposits around the globe. We see a boom in this market if somebody wants to tackle that. Indium is an interesting thing. Average price for indium is $160 a kilogram. Indium is used in LCD screens. So the key topics here, the key words that we look for whenever we try to find opportunity in these things is we look for anything that talks about cell phones or liquid crystal displays, anything that talks about solar cells, anything that talks about solar period, anything that has the word circuit breakers or circuit fuel cells in it, any the term fuel cells is actually going to create a tremendous demand for products in the future. Indium comes as a byproduct of zinc ore. Lithium, she talked about that. We see that as an exploration boom. Lithium has a price in the $13,000 a metric ton range right now. Lithium, I'm not going to talk about that anymore, but you can see from this demand chart that the demand for lithium is scheduled to go up, and I don't think it's going to see a break in the demand for the next 10 to 15 years for sure. This is lithium around the world, different supply and demand. We're not going to talk about that. Magnesium is an interesting thing. $2.35 a pound. If you want to try to find a nice magnesium deposit, dolomite, magnesium it's actually included in seawater as a component of seawater, but dolomites, magnesites, brucites, olivine, they're all magnesium rich, and you can go in and mine those. Those are the types of commercial deposits you're going to find. The interesting thing about magnesium is there's one domestic producer in North America, the United States, not North America, but in the United States. And magnesium is very important to the production of titanium. And titanium is an incredibly important metal for our economy. We're going to talk about it a little bit. Magnesium is highly recyclable, and we see a great opportunity in that marketplace. Manganese is very recyclable. $6 a metric ton though, so you're going to have to find a lot of manganese to make it worth your time. Niobium, $160 a kilogram. Most of it comes from Brazil. So a lot of it comes from Canada. Some of it comes from Canada. It's recyclable. We see an opportunity in this marketplace. Platinum, groups of metals. We see iridium, palladium, platinum, rhodium. Prices from $7,500 an ounce to $1,700 an ounce for palladium. It's located around several different places around the world. Australia, North America has some of it. Not a bad practice to try to go out and find some of this as well. Potash, big mines in potash. North America, Canada's the #1 producer of potash. Used in fertilizers. Potassium has potassium in it. It's actually critical for fertilizers. Critical for the human race. Good potash mine can make you a lot of money. Rare earth elements, you see a map there, it shows where they're located all around the world. From $2 a kilogram to $510 a kilogram. They're hard to come by, but you can find them, and if you want to go try to find them, there's jobs out there where you can use your geology expertise and you can work for companies and go mine this stuff and go get it out of the ground. Rhenium, $1,300 a kilogram. We see a lot of opportunity there. It's used for semiconductors. It's used in spectrographs, jet engines. They make super alloys out of it. It's also used in unleaded gasoline. Scandium, big market for scandium. Found in Iowa, Arizona, Illinois, and the major producer is China. Selenium, $50 a kilogram. Russia's a major provider. Canada's a major provider, used in tires, plumbing fixtures. Selenium's a byproduct of copper refining. Strontium, very interesting metal. Sells for $6 a kilogram in 2020, mined in Mexico, Germany, and China. Go find yourself a strontium mine. You'll do well with that. Tantalum, interesting. It's mined with niobium. And it mostly comes from Brazil. You see a price chart down here in the left. Sells for about $1,500, $150 a metric ton. Actually, $1,500 a metric ton, $190 a kilogram in 2020. Pretty high priced product. Most of it comes from China. I'd say a lot of it comes from China. Most of it comes from Brazil. The major producer is, as Edith said earlier, is in the Congo. Tellurium, very interesting, $60 a kilogram, located all around the globe. Not a lot in South America, but it is a pretty interesting product to go find. It's used in steel making, used in solar cells. That's a key word there, and we found a lot of opportunity there. Tin, I've had a couple of tin deals presented to me in the last year or so. Used in containers, highly recyclable, the second most recycled metal around. You find it in steel. we find tremendous opportunities in the tin market. The $8 a pound, and actually it's priced in a very high priced marketplace. So it's $16,000 a ton kind of thing. Titanium, very valuable. We see a lot of opportunity there. Sells for $10 a kilogram for the sponge metal, $2,600 a metric ton for the dioxide product. Comes in several different mineral compounds, highly recyclable, very important to the economy. 2020 price for tungsten is very, very important, $275 a metric ton, and you see a lot of tungsten mines and a lot of tungsten deposits around the globe. Highly recyclable. We see some opportunity in this. Uranium, know several families who've actually made their wealth off of uranium, and it was a lot of times by accident. They just happened to own the land the uranium was on. So we have mines in Wyoming, Nebraska, and Texas. Here's a map of North America uranium mines. Here's a map of global uranium deposits. Uranium, I don't know that I would want to own uranium, although the demand for it is pretty strong. Vanadium, another interesting thing. Most of it comes from China. A lot of it comes from Russia, South Africa. There's one little spot in the United States, North America, where they find vanadium. It's used in titanium. It's part of titanium alloys used in automobiles, axles. It makes alloy metals, hard metals. Zirconium is very interesting. Cubic zirconium is a diamond type product, but they use it for high temperature ceramics, gemstones, and nuclear fuel cladding. So anything you find that has the word nuclear in it, it's going to have some demand over the next 50 years. We don't really like radioactive type stuff, but it is a naturally occurring mineral, and you notice that there isn't any of it in North or South America. So zirconium is a very interesting thing, and if you want to go try to mine some of this, you're going to have to go overseas, go to Africa, or going down in Australia. That's about all I have. I do have some research that I can give to people, and if they'd like to email me, here's my emails, Paul@Ledger-Petroleum, and I'll be glad to send you my research. There's nothing formal about it. It's not a book or anything. It's just research I've done over the last few years. Thank you.
Thanks, Paul. That's great. And I just want to let everybody know and I meant to answer the question and answer, and I actually didn't. I will be sending an email to everyone with a link to a recording to this program tonight. It takes me a few days to edit it and process it, but it'll get out there. And I've archived all of them as well. So you can find them either through the AAPG virtual events page. You can find the recordings, or you can go to eLearning Corgi on YouTube, and that's a channel that has all of them. Also, please feel free to contact the presenters and ask them to connect with you on LinkedIn. It's a really good way to be in touch with them. And the show notes always have their names, etc. But I don't put the emails there just for confidentiality reasons. So anyway, well, thank you, Paul. That was fantastic. So I'd like to invite Ray Donelick to share his screen and to be our next speaker. Ray's at Apatite, and he's working with, he has a project called Bimby, I love the name, and it's big mass battery, and it's energy storage and critical minerals from mining byproducts. So you're muted, Ray.
Thank you, Susan. I'm going to share my screen now.
Great.
So I may be a little bit out of my element here, but I'd at least like to get you guys that know mining well to think a little bit outside of the box. I'm going to talk about energy storage and critical minerals from mining byproducts. The byproduct that I'm most interested in is coal bottom ash. It's a fairly hard to get rid of material and safely store through time, et cetera. And the United States has quite a bit of this stuff. There's a lot of it worldwide. Our goal my company's goal is, our mission is to store renewable energy using mining and demolition byproducts. Shown here is the Berkeley pit in Butte, Montana. I took this picture in 2017 during the fire season. That pit is about 1.5 miles across, and my company has received a US patent to take a mine pit like that and convert it into a, let's say, a renewable hydrogen storage vessel. It would be a massive vessel. We would essentially build a simulated geological gas field, if you will. We have a US patent notice of allowance on a method for doing that type of construction, and we have patents pending on heat reservoir components for thermal energy storage. Today, I'm going to talk to you about thermal energy storage and rare earth elements from coal bottom ash. Our technology is essentially a heat reservoir. I have ideas on how to construct these things, how to manipulate the materials that compose the heat reservoir, the shapes of the granules, if you will, the sizes, and augment that with various geometrical features to allow a working fluid to be moved around as we see fit. So we would build our energy storage, thermal energy storage, using coal bottom ash from the ground up. We would start with a coal bottom ash source. We would remove the rare earths, the recoverable rare earths from that material while we're moving past having that material picked up and transported. Then we would vitrify the coal bottom ash, essentially make glass marbles out of it of various sizes, and then use that vitrified coal bottom ash to build a thermal energy storage device. As far as coal bottom ash sources go, there's a lot of information out there. The U.S. Geological Survey has data repositories on various coals from various basins in the United States, the rocks that occur with the coals, and the ashes that result from burning the coal. There are also National Energy Technology Laboratory and various federal agencies have funded a number of studies looking at rare earths in coal byproducts, and trying to not only assess the resources and their potential across the United States, but can we find alternative uses for these bulk materials? And finally, utilities and miners would be a good resource for trying to learn about various coal ashes, coal beds, and whether or not there are economic opportunities to do something other than put these materials in a lined landfill. How much rare earths are we talking about? The U.S. has in the neighborhood of around 3.5 gigatons worth of coal bottom ash stored at hundreds of sites in the United States. If we take 1 gigaton of that material with an average of 750 ppm rare earth element oxide equivalent, we're looking at 750,000 tons of rare earth element oxide equivalent, or about 50 years worth of supply at current US consumption rates. Separating the rare earth elements out of the coal starts with the primary challenge, and that is purifying the rare earth concentrates from the coal ash. I meant coal ash, not from the coal itself. So we take the coal ash that's been piled up in a pond. We're probably going to need to crush it to some degree. Then we're going to need to perform some sort of mineral separations on it. That can be flotation type thing, which is a surface energy phenomenon. We could use density, mineral density differences, mineral magnetic property differences. But the goal would be to find processes that allow us to concentrate minerals that contain the rare earth elements. Once we have those minerals in hand, there are several rare earth element processing facilities pilot facilities being built in the United States right now. USA Rare Earths just opened their pilot facility in Wheat Ridge, Colorado, and that one can ultimately do the full range of rare earth elements from light to heavy. Linus Blue Line project in Hondo, Texas is a DoD funded project. Those guys are looking at mostly heavy rare earths. Linus is an Australian mining company. They have an Australian mine that produces heavy rare earth concentrate, and they're going to do some of their separation and extraction in the United States under DoD funding. The primary challenge, again, for getting rare earths out of coal ash is getting the mineral concentrates out of the coal ash. And we're in the process of designing methods for doing just that. The challenge for vitrifying coal bottom ash is an energy problem. We need low cost energy and preferably with low CO2 footprint. And so I show here the Gates funded Heliogen system. This is a concentrated solar power system with AI moving those mobile reflectors around. And their goal is to produce process heat up to about 1500 degrees C, which is about the working temperature we need to create glass from coal ash. So we see Heliogen, or there's another company in Europe, Arios Energy in Switzerland. They have a different type of thing, a Fresnel lens, where they concentrate the sunlight downward to a point. Again, they can produce very high temperatures. The goal of these companies is to replace metallurgical coal, that sort of thing, in iron ore manufacture, glass making, which is our interest in it. So I imagine they'd be interested in talking with us. This is my last slide. The benefits from getting thermal energy storage and rare earths elements out of coal bottom ash. We can have on-demand renewable energy. I'm envisioning thermal energy storage, perhaps seasonal for northern communities, collect sunlight during the summer, heat up a large mass, and then you can heat your city or your town and perhaps some greenhouses with that heat during the winter time. That offsets CO2 emissions. That's another benefit. If we get rare earth elements out of coal ash in the United States, that provides us a US source for meeting US demand, and it does so without creating a new mine. And by not creating a new mine, we're offsetting the need for new raw materials. We're also consuming waste. We're decreasing landfill space that's required, and we can remediate land and groundwater. It was shown earlier, the arsenic contamination or arsenic in groundwater. Arsenic is a big issue related to coal ash storage sites as well. And that's pretty much it. Thank you, and I look forward to questions if there are any.
Great. Well, that was really interesting, and we'll keep the questions until the end. But I just wanted to, wow, that's incredibly interesting. And anyway, looks like, Ashley, do you have time to do a little bit? Is Ashley still here? Looks like Ashley took off. Well, that's too bad. She had to drop for she had a presentation would be over by 8:05. So she hasn't. Well, I guess Ashley's gone. That's too bad. So anyway, so we'll have a little bit more time for questions. So let's start out with some questions.
Hey, I've got one.
Okay.
This goes back to, I think, Paul, and he was talking about the price of aluminum. And a few years ago, Ford Motor Company decided to started making their Ford pickup bodies out of aluminum. Now, they promoted that. Their advertising indicated they did that because it was lighter and fuel efficient. But then listening to that, I wonder if the underlying reason for doing that is the cost effectiveness, that it would be cheaper to build an aluminum truck body.
Yeah, I don't know the answer to that. I know that aluminum is it's not as cheap as steel. It's easier to work with than steel, but it's not as cheap as steel. So we can buy steel in today's market for, nickel a pound. as opposed to 65 cents for aluminum. So
My son has a Ford truck. I guess he bought it last year, so it's pretty new. Recently, we had a hailstorm. I was over at his house. It started hailing. It was rather small, but he was super panicking, thinking that the aluminum body on that truck would be more susceptible to denting than the steel would from the hail, but it turned out okay for him.
yeah. One of the interesting things that we've noticed that the Chinese are doing is they're going all over the world buying up these resources. They're buying up the land, going into the Congo and going into Central and South America, and they're actually putting a tremendous amount of funds out and using some of the Saudi money to go out and actually buy these resources and actually control them. And if we don't step up to the plate, we're going to be sucking the hind tit on that stuff soon. So.
Yeah, Paul, turn on your camera and we can see you.
Okay.
But yeah, you might go into some of that because that's, I don't know if you're familiar with the Chinese Belt and Road Initiative, but it's an infrastructure project. It's kind of a little bit like the Marshall Plan, but a lot of it's in Africa, and the infrastructure is provided, and the payments are often and the loans are made, and the payments are collateralized through the critical mineral.
Right. So they're taking control of those. That's correct, and they're doing it in very sly ways in a lot of places.
Yeah, there's been, and you know what happens and it's kind of unfortunate. In 2008, 2009, after the world financial collapse, the World Bank and IMF and other entities stopped making loans to countries, for example, in Africa that had a bad credit rating or inability or unwillingness to pay when things got difficult and there was like a change of government. And so so what happened is that there was just like no infrastructure for many years. I mean, 5-10 years. So when the Belt and Road Initiative came around, it was like really attractive to countries to be able to have like brand new airports, to have tourism, to have roads, to have electricity, to have hydroelectric dams. And they do that in South America as well, and also in Asia, Southeast Asia. But in particular, for example, in Ecuador, it was collateralized through oil. And so that's just been very challenging for the countries because they were hoping to sell their primary product for social services, to support social services. And so when that went away, it created all kinds of issues. Anyway, it's ongoing. I could talk forever about that, and I won't. But at any rate, so we have a question. Anyway, I interrupted you when you were talking about to ask you to leave. So you want to go a little bit more into what are the things that are happening in Africa? Which specific countries?
I don't want to. No, I just know that I have some friends from the Congo, and they've actually been run out of the Congo because of the foreigners coming in and taking over the country. So they tout it as a religious war or religious genocide type of thing, but it's not. It's way more than religion. And the Chinese government is pouring a lot of money into that part of the world, Rwanda and Congo and that whole area. So very interesting. The whole concept is, yeah.
Yeah, I highly encourage people to invest into research it. It's multi-pronged. Okay, so John McLeod asks, what is the critical mineral content of oil field brines?
Susan, would you like me to take that?
Yeah, that'd be great. Go ahead, go for it, Edith.
And certainly, I mean, it depends on your definition of critical minerals, but from my perspective, as those minerals that are in short supply and growing demand for energy storage, certainly there are oil field brines that have significant lithium. problem with the economics there is the gathering costs are so high compared to the spodumene mines in Australia or the salars in the lithium triangle. So you're competing with something that is much more highly concentrated. Now, there are thousands of small patents in process for creating a well site extraction method. And if that nut is cracked and we don't have to move all the fluid like Lithium America is doing to their big pilot plant in South Louisiana, then that's a whole new economic picture. But right now, if oil field production is ongoing and the lithium is simply an added value to the oil field, there's some possibility there for an economic driver. But if you're just producing base metal brines to extract the lithium, they're not going to compete at a commodity level. Yeah, I mean, it's yes and no is the answer. There are some projects that are ongoing that are combining geothermal circulation with lithium stripping, because there you're actually introducing fluids into the hot rocks and recirculating them. So there's enough fluid volume at the geothermal well site to make that begin to be attractive as an investment.
Yeah, thank you.
That's super interesting.
Yeah, the only other use I know for oil field brine is a substitute for Roundup. That was kind of
I mean, it's, I early in my career, I did a lot of saltwater spill studies. I'm like, yeah, it's a long-term solution for sure. For every grant. Okay, so, Ursula Hamas has a really good question. Very important. I'm wondering about the half-life of batteries and solar panels that were generated from these minerals. Would you be able to recycle a lot of the waste that's being generated?
Yeah.
Edith, you want to take
Would you like to take a stab at that, and then the other fellows can have at it too?
Yeah.
You know, if I'm not going to get the numbers right because I don't know my ore grades, but electronic waste, you know, your iPhone that you throw away every day, all the Internet of Things, your computer screens that go to the electronic recycling, piles of electronic waste actually have a higher gold ore grade than most ore deposits being mined for gold today. So these piles of electronic waste, you know, we've been accumulating them for 30 years, and what we're finally beginning to see, which is also going to take hold as solar panels begin to mature, is mining waste. And where this is being adopted by corporate, global corporate businesses at large is the concept, if you want to do some research on this, is to look at the circular economy concept. So, for example, companies like Schneider Electric, which if you look around your office space right now, probably most of the widgets, the wires, the plugs and stuff in your walls come from Schneider. And they are now beginning to look at each single step in the life cycle of a product as contiguous. So they're as worried about recycling the metals and the minerals in their components, which include, of course, solar panels, but they're one of the biggest solar panel distributors. You know, solar panels today are just like electric parts that you get at Lowe's. I mean, they're plug and play. So companies that are in that business are already starting to look at that waste stream as a supply stream. So there's a lot of business opportunity there. One really interesting note here in the U.S. is that California has now declared solar panels. You know, solar panels have a guaranteed life of 25 years. Most of them last a lot longer than that. So you're talking about a long recycle time. But California is probably further down the road than almost anyone else is installing solar panels, having them, you know, come up to be waste. And they have just declared solar panels to be I forget what the category is. It's something like useful waste or material waste, but essentially they have to be treated like anything else. They have to be put through a recycling phase. So I think that's what we're going to see as we begin to see the installed solar mature. We're going to see both the manufacturers want to reclaim that very high-grade material, and we're also going to see policy making dictate that the components need to be recycled, which is certainly something new for the energy business. I mean, we don't, we plug our wells, we don't recycle the steel, et cetera, that goes in the ground in the oil field. But I think when we start to look at renewable energy infrastructure, we're going to see recycling and the circular economy. That's the buzzword to read about in corporate literature. We're going to see that pick up.
Oh yeah, that absolutely. Great answer. Okay, so Ursula has another question, and I think this one would be great for Paul to answer. So which metal,
Which metal what?
you are paying attention, I was going to,
Yeah, which metal what?
which metal would you be inclined to recommend as the up and coming investment?
Oh, in today's world, lithium is the number one material that you'd want to go try to find. One of the interesting things about it, the second most recycled thing on an automobile today besides the motor is the catalytic converter. And it has a lot of these critical minerals in it. They price up to, some of them above $300 each for the catalytic converter on an automobile. And it's because they're made out of these critical minerals. But if I was picking one, I would actually try to do something around magnesium, lithium. If you can stand cobalt, you can do some good with cobalt. You just have to do your own research and use your own background and your own knowledge. My background was in mining and recycling. I was the recycling coordinator for EPA for 7 years in Region 6 in Dallas, and we recycled we learned and taught people how to recycle all these products. So, and when Edith was talking about recycling a minute ago, it's a huge stream of wealth for people. We throw away so much stuff in the United States and North America that needs to be recycled and needs to be reused. And steel's just one example. For 2 decades, scrap steel was the number one export from North America. It's not any longer, but it used to be. So recycling is actually one of the biggest things that people can do in today's world, and there's a huge amount of wealth there to be had.
That's great. Well, it reminds me of what Edith opened with, is the idea of mining.
Yeah.
Can
I add one thing to that too?
Sure.
To the investment question. Don't forget that this world is not driven by the commodity the way oil and gas is. It's a technology play, right? So you can invest all along that supply chain that I showed in the one slide. You can invest in the mining side, but that's only a tiny piece of the value. You can invest in people who are manufacturing that bespoke graphite for the very specific battery specs that they have to meet, and that's where a lot of value is added. So if you can find a good investment there, you can invest in the installation and project management side in a company like Schneider, like Nextera, like Ameresco. I mean, so that's where all the technology value is being added. So, it helps if you think of this new energy stream, if you're thinking of it in terms of investment, don't limit yourself to the commodity, because that's only a very, very small piece, not like in oil and gas where that's where most of the money is.
That's interesting. That's a really good bridge for a lot of people who are basically coming to this from oil and gas. Okay, so here's a question I think maybe Ray can answer. So Daniel Callanan mentions RRE aren't rare, but require heavy processing with a bunch of RA waste. Do you have an opinion on the feasibility of processing it in the US? Mountain Pass Minerals has a facility, once bankrupt, in California.
Yes, the toxic kind of residuals from the processing rare earth elements is one of the reasons why China has kind of done a lot of this stuff domestically. It's also my understanding, by the way, China has thousands of US patents on their methodology. But regarding doing this in the United States, one of the ideas I have, and again, I'm thinking outside the box here, is if we are going to vitrify the residuals from the rare earth element mineral concentration steps, then we can also basically include in that glass any toxic material that's generated, or decompose it or render it inert. So I absolutely, the toxicity of the processing is an important thing. National Energy Technology Lab is also funding some various laboratories that are trying to do this in non-toxic ways. So there are people looking at different streams for generating these materials.
That's super interesting. So here's another comment that for Daniel. EnviroLeach is trialing, testing cyanide-free technology for electronic waste processing, the gold extraction. That's interesting, worth checking out. Okay, so I have another question here. Let's see, scroll down. This is for Ray. Can broken up solar cells be used for heat storage?
I have to unmute. Beyond broken up solar cells, my understanding that most solar cells are, a mixture of plastics and various thin films. Those things aren't very stable thermally. The flip side, the interesting thing though is I would go to windmill turbine blades, and that's going to be a big waste stream that humanity is going to have to deal with at some point. Texas is going to be covered in that stuff soon. And what you have is fiberglass, and we envision trying to insulate our thermal energy storage using ground up windmill blades. But I haven't looked into that at all, but there's no reason why not to imagine it at least.
I've seen people like fancifully put together plans for housing using them, but not grinding them up.
Yeah.
Super interesting. Okay, so here's another question. Maybe Paul could answer this one. Do you think that cheap oil is a barrier to developing sustainable energy sources and its storage?
Yes, certainly is. Cheap energy is very much a barrier to that. But so we're working on building a solar farm right now, and the price of solar since I've been working on this project has come from 7 cents a kilowatt to 3.5 cents a kilowatt. So it's not as big a barrier as it used to be. Cheap oil is a big barrier, and it is a barrier because it's in place and entrenched. But as solar prices come down and solar panels come down and we can build a solar farm today for half what we could build one for 7 years ago.
That's a really good, interesting point. Plus, well, with what's going on in shale, I think that within 18 to 24 months, gas and oil are not going to be so cheap anymore.
That's right. That's right. And that will change the entire solar array and wind field for sure. Yes, that's correct.
Interesting. Okay, so we have a question from Alexandra Miselski. I'm a rookie. I come here with a background that is not in geology. Rather, I was a metalsmith jeweler and have an appreciation and some understanding of minerals. What kind of entry into this field is viable? It is so fascinating. I'm finishing grad school soon. That's right, Alexandra. Congratulations.
Can I take that one?
Sure.
I think, and I apologize, was it Alexander or Alexandra?
Alexandra.
Well, I think that your skills are going to be uniquely suited to the processing piece. And if you want to get into some really interesting startup chemical material science research, one of the questions that came through earlier that I just answered online was about energy density. And the things that are being done now at the nanoscale to improve energy density, because of course lithium-ion batteries are still just a fraction of the energy density of gasoline, which even though you don't have to replace the tank of gasoline every time you use it up, you still can only pack so much energy into the battery on the floor of your car that takes up the whole car. So researchers are really working and at the nanoscale, at the layered scale, at the glass electrolyte scale. So if you have an interest in how materials fit together, there's some fascinating work going on.
Oh, that's cool. Thank you. Thank you, Edith. So we have a question. How much potential helium do we have? So I'll open this up to whoever wants to answer that.
Well, my map showed that I put up that potential helium globally is 200 BCF, I guess. So it's not anywhere near like natural methane gas is, but North America has 140 BCF of helium. And I was just talking to a man a minute ago, and there's discoveries going on every day. So we really don't know the answer to that question.
And I'd like to encourage people, if they are interested in helium, to sign up for the AAPG annual convention, which will be September 29th through October 1st, completely virtual. And we'll have a live panel on what else can you produce from gas. And 3 people will be talking about helium. And they're also talking about argon and other kinds of things. Okay, so Alfonso Ibarra says, in the near future, do you see more energy companies using renewables as well as batteries to power and optimize long-term oil and gas operations?
This is Paul. Yes, we actually have a project on the table right now where we're actually installing solar to pump oil wells. So yes, the answer to that is yes.
Yeah, that's been around for a long time, especially for any of the control systems.
Yeah, and we're actually putting in solar pumps that are driven by solar panels.
That is amazing. That's super.
Yeah, it is. And we're able to actually pump fluids from 4,000 feet with small solar pumps. So,
wow.
Yeah, very interesting technology. And we're actually trying to buy some fields right now where we can actually install that.
That's nice. Okay, so one last question, I think. Let's see, what did I think I missed one. Larry, are you looking at the questions? I wonder if I missed one. If I missed one, somebody just shout out and ask easier. You can talk on, ask the question live.
My system's great.
I've been cheating and answering people online. There was one about when will be the price point where battery energy storage can compete with coal and gas.
That's what happened.
We're way past that. Yeah, we're way past that. Actually, right now, the banks and the insurers won't finance or insure coal-fired power plants anymore because they're economically so distressed. And some of the recent studies that I have seen show that the natural gas power plants that are on the books today and being built will be stranded by, sometime in the next decade, depending on their source of natural gas. So we're already there. I mean, if you look out at the utility space for news, you'll see all these huge projects being announced. The one I talked about, Susan, that NextEra is building out at out in western Oklahoma is going to be the largest wind solar storage project in the U.S. and that'll be operational in 2023. So it's happening. That change has happened. Those curves have begun to cross.
That's really interesting. So, do you think that Okay, so that kind of answers Alex Tan's question, but I'll ask it anyway. He would like to ask if lithium recycling poses challenges to lithium mining. Not sure about the cost to recycle lithium from batteries, e-waste sources, etc.
Yeah, I know some financial analysts who would say that yes, it does, and then of course I know some chemists and inventors who say lithium will be yesterday's news by this time 10 years from now. But you know, the reality of the market right now is that the lithium-ion battery is baked into the supply chain for electric vehicles, which are just exploding. So, you know, a Volkswagen building their new plant in Smyrna has already contracted for lithium from China and graphite from Mozambique, and you know, it's all being lined into spec with whatever they need. So that supply chain of minerals is there for the next couple of decades. But certainly when the turnover happens, which will be a while, you know, before these batteries are completely recycled, because after they're used, and you may not know this, Susan, but one of the world's largest battery recyclers is right here in Oklahoma City, Spears New Technology, and they take old EV batteries. They take all of Chevy's and a lot of Nissans, and they pull them apart and refurb the cells and build them into towers for energy storage. So there's kind of first they're refurbished and used again in electric vehicles, and then the parts are disassembled and they put them together in storage towers. So, you know, there's a lot of steps to the life of the battery, but when you actually get to the end of it, there are people on the financial markets that think that recycling phase will you know, put a crunch on lithium mining for sure. That's why thinking about this as a circular economy is so important.
So yeah, that's really true. And then also last week we talked about new images and space images and different information we could get about mines, potential mining resources, and makes me realize that, okay, thought again about a new mine that's going into production in northern Nevada. So in your Nevada, it's a volcanic deposit that has lithium. So anyway, it hasn't gone into production yet, but they are working on it. So I want to thank our presenters today, and also, unfortunately, Ashley had to leave early, but what I'm going to do is contact her and see if I can record her presentation, and I'll upload it, and I'll make that available to everybody else as well. So I'll have more content. Science and Technology Showcase. So basically, well, I want to say thank you to you, Larry Davis, and to you, Paul Thomas, and you, Ray Donelick, and finally to you, Edith Wilson, out of order from the presentation, but in order on my screen. So just any final thoughts?
Just feel free to reach out on LinkedIn, anyone, if you have questions or you're interested in connecting with someone and anything we've talked about.
Great, absolutely. So,
Susan, my final thought is this is a tremendously dynamic time in the critical minerals world, and people need to be out there working on it as hard as they can, because it's an exciting time, because there's a tremendous amount of growth in the marketplace, tremendous amount. Even though oil and gas is kind of on its fanny right now, there's a tremendous amount of growth in other minerals, and as a geologist, other minerals ought to interest you just as much as oil and gas do. So
that's a wonderful final closing thought. So on that, thank you, everyone. I'll be following up with an email, and stay in touch. Be back next week for more. Bye.
Thank you.